quick reminder of what happened last time. So we defined the abelian for topological space X. We defined a sequence of abelian groups labeled by non-negative integers Cn, which we called this was a singular chain complex. And so for each n, this is a abelian group generated by all possible continuous maps from n simplex to X. And then we defined a boundary homomorphism, which was a map from Cn of X to Cn minus 1 of X. And then we define a singular homology, Hn of X. This is a abelian group, which is defined as a quotient of the kernel of Dn by the image of Dn plus 1. The fact that this is the image is a subgroup in the kernel, this follows from the fact that which we showed that the composition, the following composition is zero. Okay. So this was our definition. Okay, now we would like to, as we did in for fundamental group, we would like to learn how to calculate these things and show some properties which will also help us calculate. Okay. So let us start with the following proposition. So let X be a disjoint union of X alphas, where each X alpha is a path connected component. And then taking the for each n the nth single homology of X is a direct sum of nth single homologies of X alphas. Probably the proof is fairly simple, essentially from definition. So we know that so for any sigma, sigma which generates which is a generator in this group, we know that it's it's defined on a simplex. It's a function defined on a simplex which is path connected. Therefore, there exists a unique alpha such that the image of the sigma is completely inside the corresponding path-connected component, right? Because otherwise there will be a path between different connecting components. If you compose this path, any two points here can be connected by paths. You can compose this path to this path. Okay, and so for any sigma is its image is inside X alpha, so therefore it follows that all these groups they split into a direct sum of the groups of singular chains for each path-connected component, right? Because each of these guys belongs to one of this, and the decomposition and it belongs to a particular subgroup like this. And okay, and then it's enough. We also need to show because we need to show that this boundary homomorphism when I act on this direct summary boundary homomorphism, each component will be. So the image of each component will be in the image of the corresponding component for when I replace n to n plus 1. Namely, so we can do this by noting that so if I do, so I just can use the definition of the boundary homomorphism, the n. So I take some sigma here. Let me take sigma, and so I take sigma in a particular component here, Cn some x alpha, and so by definition, the boundary homomorphism is given by this formula. So if I choose the vertices of my simplex denoted by v0 to Vn, then the boundary homomorphism is defined like this. So I take an alternating sum of extension of the sigma to a subsimplex where I remove one of the vertices. Of course, but then of course I see that if sigma if the image of sigma was inside x alpha, the image of this restriction will also be inside x alpha. So this means that this is also belongs to Cn minus 1 of x alpha, because its image is automatic. Okay. Therefore, continue here. Therefore, this means that the n of the image of the whole group is inside Cn minus 1 x alpha. And therefore, when I calculate this quotient, when I calculate this quotient, the quotient also splits in the direct sum of quotients.
Why do the quotient splits also?
Well, the kernel splits into the sum of kernels, and this image splits into the sum of information. And of course, the equivalence, or the quotient defines the equivalence relation. I the image splits into the sum, but this is so the quotient defined by certain equivalence relation can add elements of the image to elements of this subgroup. But of course, the elements by adding, so these elements is represented by some by a sequence of elements, so that each of them in particular component here, and the equivalence relation means just they're all pairwise equivalent. Well, this is more or less tautological. If you want more explicitly, the kernel element of Cn that can be realized as equivalence. So first, when beta is in the kernel of Dn, well, Dn defined for x, this is equivalent to beta alpha in the kernel of Dn defined for x alpha. The same for example. Gamma alpha, and the equivalence, the quotient is this equivalence equation. Sorry, beta is equivalent to beta plus gamma is equivalent to condition that beta alpha is equivalent to beta alpha of the alpha. Once we show the d-acts between the corresponding components, we automatically know this is automatic. So another statement is the following. So suppose X is not an empty space and X is plus connected. Then we want to show that the zeros homology group for any such X is isomorphic to Z. Okay. So to prove this, let me consider the following map. Auxiliary map should be useful for us. So it's a map from C0 of X to Z. So before we know that in the chain complex there was a sequence of differential and the d0 acts on C0 of X by as 0 by definition, but instead we can define sort of a map epsilon to Z, and the map is defined as follows. So suppose, so we know the elements here are linear combinations of singular simplices with integer coefficients, and with the result of this map is just a sum of these coefficients. So each sigma I is just a certain map. Well, in this case, so this is a C0. So this is a map from delta 0 to X. And this is just, we know for in dimension 0, the simplex is just a point. And we know that if X is not empty, this means that this map is surjective. Well, to show it's surjective, it's an absence of, well, by definition, it's a homomorphism. So it's it's enough to show that we can obtain 1 here, but we just take, I mean, there always, if this is non-empty, there always exists a map from a point to non-empty space. And we can just take any such map as coefficient 1. So this is surjective. This means that if I consider the quotient of this abelian group by the image of this map, image of epsilon, which we show that this is Z, this will be no. So if you consider the quotient of the kernel of epsilon, this will be the image. This should be the image of this map, and this is, we know that it's Z. Now we want to show that the kernel of epsilon is the same as the image of D1. So once we show this, we will essentially immediately prove the statement, because we know that the kernel of D0 is the whole space. So if we show this, it immediately show that this is the same as this homological definition. Okay, so we'll show this in two steps. So first, so D1, I remind you, D1 was a boundary homomorphism from C1 of X. So we'll show it in two steps. We'll show inclusion in both directions. So let us first show that the image of D1 is a subgroup in the kernel epsilon. Well, let us take so an arbitrary to check this. Consider the following element of this form. So consider some sigma in C1 of X. Sigma is some generator in C1 of X, which means it's the map from delta 1 to X. And I acted them by D1, so this gives me an arbitrary element in the image. And to check that this is inside the kernel, I want to show that the epsilon, if I apply epsilon to this, then I get 0. Okay. Well, let's do this. So it's sigma is a map from one simplex, which has two vertices. Let's say V0 and V1. So if I apply D1, this is by definition it's a restriction of sigma to V1 minus restriction of sigma to just zero simplex, which is just V0. Okay. And so this some generators in C0 of X, some singular simplices, and then I can just use the definition of this epsilon homomorphism. This is well, the sum of the coefficients, which is 1 minus 1, which is 0. So okay, this is a check for this. Now I want to show the inclusion the other way around. I want to show you the kernel epsilon is inside each. this will be a bit harder. So what does this mean that sigma, let me take some arbitrary sigma in the kernel, some element beta in the kernel epsilon. This means that beta is of the following form, so if I represent it as using the generators, my generators, singular simplices, this is the following form where the sum of the coefficients is 0. Okay. So sigma i's, remind you, they are maps from zero simplices to x, and this is just a point. So, I mean, these maps from a point to some topological space is uniquely determined by its image, by just some point in x. So each sigma I is completely determined. By the image, which is, I can understand this image as a point. Well, to be precise, it's a subset. It's a subset, it's a single point, but I can put using the notation. This is, I consider just a point, element of x. So now we know that x is path connected. And let me choose some point x0. Let me fix some point x0 in x, and then it follows that for any I in this sum, there exists a path Ti in x such that it starts at some fixed point x0 and it ends at this point sigma I delta 0. But now I can notice that this path, which is marked from interval to x, I can interpret it as a singular one simplex, because this is I can understand this interval as a delta 1 with vertices, so v0, v1, which is just 0, 1, sorry. So if I understand this as a element in C1 of x, this way, I can calculate the value of the boundary homomorphism of each of these Ti's. And so by definition, this is a restriction of Ti of the end of the interval, which is 1 here, minus extinction of Ti is the beginning of the interval to 0. And this is so I can interpret this x0 point as a value, since we know that there is one-to-one correspondence between points in x and singular zero simplices. I can understand that as a value of this point as a value of some singular simplex sigma 0. See, and then this will be so this restriction is just sigma I, and this restriction is just sigma 0. Okay, and then so if I take the following, let me take D1 of the following linear combination of TIs. The sum with the coefficients Ni is the same coefficients which appear here. So then linearity is like this. Well, we know that so we know that this is 0, right? There is no second term actually, and this is our answer. We show that if you take some arbitrary element beta in the kernel, it will be inside the image. So finally, by combining this two, so we learned that the kernel of epsilon is the same as the image D1, and then well, but this is just a definition, the cohomology of x 0, zero's cohomology. Sorry, zero's homology of x is the quotient of the kernel. 0 divided by image D1. So D0 acts trivially on C0. So this is the kernel just whole group C0 of X, and image we learned is the same as kernel. And this is isomorphic to Z. Questions?
This D0, how is it defined?
It's defined by 0 being 0. Well, I wrote here, the sequence was like this. 0. This is just because there is no -1 synthesis. This is an empty group. C minus 1 is an empty group. So now let us calculate something simple, the homology of a point. We want to show that, well, it's, for n equals 0, it's that, which is an agreement which we showed before, but for all other n's, it's trivial. So how do we calculate this? So for any n, so this is a point, so singular, so the singular simplices, there are maps to a point, but because they always exist, there only one map to a point. So for any n, there exists a unique sigma n, which is a map from n simplex to x, which is a point. This means these groups are all just generated by a single element, just isomorphic Z. Okay, so we know the group Cn. Now we want to know how the boundary homomorphism acts. Well, it's enough to do this on the generator. So if we act on sigma n, deal on sigma n. So by definition, this is the following alternating sum. So here we want to consider the restriction of sigma n to some to a phase, right? To a particular phase. But of course, all restrictions, since there's a unique map, they're all the same. They're all the same, and they're equal to sigma n. All this restriction equal to sigma n minus 1. And but this is so if n is odd, everything here cancels out, right? And if n is even, everything cancels, but the well, there's only one term left, right? It's just so the singular chain complex looks as follows. So we have the following sequence. So this is our C0, this is our C1, 2, so they all these groups equal to Z. And what about this map? So this is 0 by definition. This is so n is, so this is for n equals 0, so n equals 1. When n equals 1, it's odd, so it's also 0, right? So for so so for n equals 2, this map takes me generator here and gives me the generator here. So this map is just identity. And again, this will be 0, this will be identity. Okay. So now, well, okay, so well, let me consider first H0. H0 of a point. So this is a kernel of this map, which is Z, divided by the image of this map, which is nothing. Okay, so this is Z. Okay. So 0 was a bit special. Now let me consider all Hn of a point when n is positive. So now let me consider now positive n's, and first consider n odd. But since because of this periodicity, it doesn't matter which odd we take. So let's take, for example, this guy here. It's the same for C3 is the same. So the image, so the kernel, so here is the kernel of 0 is Z, and the image of identity is also Z. So divided by Z is 0. And now consider Hn of the point when n is even. So this is, let's take here, for example, so the kernel of identity is 0, And the image of 0 is also 0. Any questions? Now I want to do the following some algebraic definition, and we already had this, but this, I mean, we will need it a bit later in our course, but we also will need it in this definition in the third problem of the homework. But this is some terminology which we later will use a lot. So it's better that you familiarize yourself with this. Sequence of homomorphisms. Between groups. Well, for us later this would be for abelian groups, but you can consider general groups. Between groups n is called exact if kernel of alpha n is the same as image of alpha n plus 1 for any n. So you can already see some relation to what we will be doing later. So we make the following remark: if a chain complex is an exact sequence, this means that the corresponding homology groups are all trivial. Because the homology group like that is this quotient. The quotient of the kernel. So there's some nice particular situation of exact sequence, which is called short exact sequence. An exact sequence on the form by 0 here, I don't know the trivial group. If there's just three non-trivial entries, this is called a short exact. So what is the example of short exact sequence? Than before. We take 0, z Z2. The first map will be, the first homomorphism will be multiplication by 2, and the second homomorphism will be taking number modulo 2. Namely, here, the integer is split into twice this integer. And here, if I take some integer, we go to M2. And you can see that the kernel of this map is exactly the image of this map. Okay, to make your life easier, almost easier, we can give you another one. Here also, so this is numbers modulo 2, this is numbers of modulo 4, and this is numbers modulo 2. So here I take again multiplication by 2, and here I again take modulo 2. And this is also an example of short exact sequence.
Is that free in between? The definition?
The definition of short is that they're exactly 3 non-trivial, and well, there are 5 terms, but the first and the last are trivial groups. So in particular, this means, I mean, here it's also satisfied, right? Because the we actually have to check that this is also satisfied here. So we know that the kernel of this map it should be the image of this map. You know, the image of this is of course trivial. So but the kernel is also trivial. And here we know that so this essentially means that this map should be injective, and this map and similar here. So we want the kernel of this map, which is the whole space, and this is 0, should be the same as the image of this map. This means that in particular this map is surjective. So exactness is satisfied at all 3 places.
If there is nothing right as morphism, we should expect a kind of embedding or something like that.
I mean, this map, as we argued, is always injective. Is what it is.
Even the okay. But this we should add the morphism to for it to be precise. I mean, like this.
Well, these are, I mean, the part of the data are these homomorphisms. Well, this automatically given, right? There is unique map from 0 and unique map to 0. I mean, this is the homomorphisms here are the part of the data of the sequence. The sequence by definition is a sequence of groups and sequence of homomorphism. When we're talking about sequence, I mean, there are some maps. But I mean, there are also condition. If I take, I mean, even without specifying maps, only certain triples can be realized in. Only certain triples of group can be realized in the short exact sequence. For example, here, see, for example, I can also consider the following short exact sequence. In the middle, I take the same A and the same group here and the same group here, but in the middle, I take instead of Z4, I take Z2 plus Z2 as the then this map I realized by taking element. So elements here are pairs of numbers mod 2. So this map I can realize by taking this A to pair A, comma 0, and this map, so some general pair is taken to B, the second component. You can see that this is also example of a short exact sequence. It works like this. And you can argue that in this case there's nothing more. If you fix A and C to be Z2s, there are only two choices of abelian groups. Okay, now, so this is a bit of algebra. So now we're coming back to our theory of homology. So many properties which you want to show, they're kind of similar to the properties of the fundamental which you had. In particular, we want the polynomial groups, there was a notion of push forward. So there was a map between topological spaces, there was induced map between fundamental groups. Similarly here, we want to construct the notion of push forward. But so before doing this, we can define induced map. So for some continuous map between x and y, we can define induced map, which we denote by F sharp, between the corresponding singular chain complex. It's a map. It will be a homomorphism from Cn of x to Cn of y between these abelian groups, and it's defined by the following. So the elements here are formal sums of singular simplices, sigma I, and they are mapped to images the following. So each sigma I here is replaced by the composition of sigma I is F. And of course, so since this guy defined a map was a map from delta n to x, this composition will be indeed a map from delta n to y, which is an element here. So this makes sense. Okay. Now we want to show the following property. Small. So the singular chain complex for x is the following form. I'll just write some part of my sequence, and here there will be a reduction of boundary homomorphism. So in principle, we want to, these are different maps, so before we denoted them by n, but it's always, in the context, from the context, it's always clear that where it acts, on which group it acts, and where is the image. So you can suppress, I usually will, in many cases I'll suppress the index here explicitly. And similarly we have for my space y, the following sequence of boundary homomorphisms. And here I also will denote them by D, because this is also different maps, because they act between different groups. But the same notation. And so now, and we defined the maps F sharp like this. And the statement that this is the diagram is commutative. Commutative means that for any square like this, if I go like this, if I take some element here and act on it by this map and then this map, or like this and like this, I end up with the same element. This is what I want to check. Well, let me consider this square instead. Okay. So let me take some arbitrary. Well, it's enough since it's all homomorphism. It's enough to check it on generators. So let me take some generator in Cn of x, which is the map from this is a proof. Which is a map from delta n to x. Generator in Cn of x. And so let's see what happens if I go like this. So I want to calculate f sharp of d of sigma, right? Okay. So let's do this. So I apply the. So again, let me choose the denote vectors by 0 the n here, and I use a definition of d, the restriction sigma to a face. Well, this is then I use the fact that well, by definition f sharp is linear, so you can instead write like this. And well, that's it. I mean, the f sharp of course taking well, f sharp is just acted by composition, right, on this guy. So this is but taking the composition and then restriction is the same as taking the restriction and then composition. So this is the same as namely the same as minus I. So I can first take composition and then take restriction. This is d of f sharp. So we showed that we get the same by going this path, but we get the same result if you went like this. So we showed this commutative. Questions?
Did you give a specific name of the f sharp? Like push forward or something?
Well, not quite. It's well, it's closely related to push forward, which we'll define in a moment. One can tell that say it's induced map on the chain complex. Map induced on the chain complex, on the single chain complex. Induced. Okay, so and okay, so now I want using this statement So again, define a push forward or mapping just on homology, shown by F star as before as for fundamental group. And so it's defined for any n. So here again, as for D in the previous proof, I suppress explicit. So this was a separate map for each n. Okay, so can we finish? Will we finish? So this takes well, okay, so let me remind. So this is a kernel of D. Well, let me here write explicitly for a moment. Kernel of Dn, which is corresponds to space X divided by the image of Dn plus 1, also divided by space X. And this is kernel Dny and the image of Dn plus 1 y. And so elements here are elements in the chain complex, which is inside the kernel modular elements in the image. So there are certain equivalence classes. So the elements here in the group, they are represented by elements beta in Cn of x, such that d and beta is 0, and we consider equivalence class, equivalence relation corresponding to adding elements in the image. And this is we want to take this to F sharp, class of F sharp of beta. This is how we want to define. But of course, we need to check self-consistency. To finish, there's a lot of, there are two questions. First, the question, does it represent a certain element here? So we need to check that this is not, well, this, by definition of F sharp, this gives me some element in Cn of y, but we want to check, for this to make sense, we want to check this actually in the kernel of D here. So one thing we want to check, and the other thing is we want to check that, as usual, independence on the choice of representative. So if we choose a different representative of this equivalence class, we get the same result. So result is well defined. We want to check that this is 0. This indeed belongs to this kernel subgroup. Okay, but I mean, by previous proposition, we showed that this is we can exchange F and D here. So it's the same as F sharp acting on dmx. But this, you know, we chose beta to be a representative of this quotient. So this basically beta is inside kernel. So this is 0. The whole thing is indeed 0. Okay, so we check this. And the second point is that we want to check independence of the chosen plots. So let me take instead, beta plus dn plus 1 x of some gamma instead of beta. So I changed beta by arbitrary element in this image. So if I use this formula, this gives me a class of f sharp acting on beta plus d x plus 1 gamma. This is the same as class of f sharp. So using the fact that f sharp is homomorphism, this is f sharp acting on beta plus f sharp dx and plus 1 gamma. And here again, using the previous proposition, I can commute f sharp and d to the same as dn plus 1 x. Y f sharp acting on gamma. And since here we're taking the class, goodness class modular elements in the image of dn plus 1, this is the same as f sharp of beta. So we check that this is independent on the choice representative. So f star is indeed well defined. Questions?
Why is the f sharp of 0 equals to 0?
F sharp of 0 equals 0 because f sharp is a homomorphism on billion groups. By the formula we defined f sharp, it's automatically 0. Just because the 0 is a combination of singular chains with 0 coefficients. Any other questions? Okay, so now, as for fundamental group, we want to show some nice properties of the push forward. First property is the following. So, again, it's a behavior under the composition. So suppose we have a triple of topological spaces and we have a map from X to Y and then a map from Y to Z. And we want to show that the push forward, or we can go directly from X to Z in the composition. We want to show that the push forward of the composition is a composition of push forwards. And the second property is that the identity map, its push forward is identity homology. I mean, they more or less follow from the definitions. Nevertheless, again, it's well, we have some formula like this for this equality of homomorphism. It's enough to check on generators. So let me take some singular simplex in X and. We want to. So we know that. Let's do this way. So we know that we consider compositions of maps F and G first, and then compose it with sigma. This is the same as composing F is a composition of G with sigma. And so by definition of sharp and G sharp, it follows that well, they just defined by taking the class by taking the compositions of this generator of these maps, right? So it immediately follows that the map induced by the composition is the same as the composition of induced maps. Well, now you can just use definition of the push forward. So the definition of push forward was just by applying this sharp map, I mean the induced map in the on the chain complex and taking its equivalence class. But since the composition here the composition satisfies this property, then we immediately have that. And if we apply the definition of start for this guy, we get composition. We push forward as a composition. If we apply the definition of F star and then G star to this, then we get G star. Well, same second part. So we know that if we consider identity on X, so it's induced map on the chain complex will be identity Cn of X by definition. And then it follows that identity on X star is identity. By looking at that, yeah, remember the definition is becomes obvious. Any more questions? But Yeah, with the fundamental group, one can make this not important remark that this means these properties Hn is a function the category topological spaces to the category of abelian groups. If you don't like category series, you can gain ignorance. So for the fundamental group, we learned that it's for homotopy equivalent spaces. The fundamental group is the same. So basically, this allows us to use the fact if we can find some homotopy equivalence and calculate the fundamental from one space, we immediately know the answer for the other space.
A question. Why the homology groups are abelian?
By definition, they were quotients of abelian groups. So Cn was defined as a abelian group. So it was defined as a free abelian group. So the kernel is abelian. The kernel of homomorphism is automatically abelian, and the image is also abelian subgroup. So this is just by construction, it's not some property you need to prove. So we want to show the following property. So suppose we have a pair of marks from X to Y. And assume they are homotopic. It follows that their push forwards are the same. Push forwards as marks. This is again similar to what we had for fundamental group. Okay, so let me start the proof. I'm not sure if I'll be able to finish today. Maybe. So they are homotopic, then there exists a homotopy. This means there exists a homotopy F from X times unit interval to Y, such that I stick F to 0. Here, this is F, and I'll stick F to 1. Here, this is G. So let me consider. I want to consider the following topological space. simplex and simplex times interval. And so if I take a subset delta n times 0 here, this can be identified. This is a copy of the n simplex. For this copy, I want to choose vertices to be denoted by v's before. But if I take 1 here times delta m, this I want to understand as another copy of simplex. So I want to distinguish it. So I want to choose vertices here because by double this. So two copies, two different copies of simplex. Well, I have to be more careful. I have to say, well, there's a when I use this campaign, when we talk about simplices in this sequence, we pick a particular order of vertices. So the order of vertices here and here, they should be consistent in the sense that if P, if I project, I can project this delta n times interval to just delta n by taking projection on this factor in the product. In the product, I want require that the projection of VI is the same as projection of WI. So if we consider this projection, these vertices they correspond to the same vertex here. Okay, in a moment I will draw an example of what's going on. Before that, let me make the following statement. So we want to consider this space, and I want to understand that this delta n times interval as a union of n plus 1 simplices with the following vertices. So first I take a sequence of vertices from this guy, V0 to Vi for some I, and then, but then after this Vi, after is index here, I take is vertex here, and I continue with vertices here. So I here runs from 0 to n, right? And there so there are n plus 2 vertices here, so this is n plus 1 simplices here. And they have, so the simplicity has non-intersecting interiors. So let me draw you an example of how this looks when equals 2. So equals 2, delta 2 is a triangle. The triangle times an interval. Something like this. So for the triangle downstairs, I pick my vertices V0, Vn. So here it's V0, V1, and V2. And here I pick vertices W0, W1, W2. And then I want to split it and represent it as a union of simplices. So first, so in this sequence, first there will be so when I equals 0, right? The first will be when I equals 0, so it will be V0, W0, W1, W2, and this is this guy. Simplex. So the second guy will be V0, V1, and then W1, W2. So this will look like this. And the finally there will be a guy is V0, V1, V2, and then W2. You can see they indeed have no intersection here. And they fill the whole, the whole space, the whole space. It's called the prism. Okay, so now we are ready to define what is called prism operator. This will be a homomorphism from Cn of x to Cn plus 1 of y. Again, it's enough to define one generator. So here the generator is a map from delta n to x. And I will map to the following alternating sum. So it's kind of similar to what the definition there of the boundary homomorphism, but not quite the same. So let me write the formula and then I will explain it a little bit. What is all defined. what happens here? So what happens is the right hand side, so it's a bit heavy formula, but okay, so how do I understand this? So first, so I consider my prism as the following space, and so sigma is a map defined on delta n, and on a product I can define the product of maps sigma and the identity map. So it will map to x. So the sigma maps delta n to x, and identity of course maps x to identity maps interval to interval, right? And then, but then from this product we have a map to y, or homotopy. So this composition is a composition like this. So the composition defines my map from the prism to y. It's called composition. And then we split our prism into vectors into simplices like this. So I can consider restrictions of this map defined on the prism on simplices of this form inside the prism. So this is so the result of this restriction. The result of the restriction can be understood as a map from this simplex, which is n+1 simplex, to y. It's a well-defined. It's indeed an element here, which I can take, and I can take some linear combinations. So what do you want to show? So we probably not going to have time to require some time to show this. So I want to show, which we will do I guess next time, we want to show this property. For the prism operator, so there is a understood as a relation between homomorphisms from Cn of x to Cn of y. And so once we show this, it will immediately follow that the property shown. So to be continued. The property to be continued.